Next, we're going to talk about phase. Now, phase is this rightmost part of our equation that measures the left or rightmost shift of our sinusoid. And in general, you know that phase can be written in one of two different units. It can either be measured in radians, I'll abbreviate that rads, or degrees. I'm not going to talk too much about this because you already know from your freshman year that you can convert back and forth between radians and degrees by either multiplying by 180 over pi or multiplying by pi over 180. And I recommend that you not try to memorize this, but you just think it through. If you've got radians and if you want to convert it to degrees, you know degrees are much bigger. So you want to multiply it by which one of these things will make it bigger. Obviously, 180 over pi. Similarly, if you've got degrees and you want to make it into radians, you got to make it a lot smaller. So you'll multiply it by the one that's less than 1, pi over 180. A fact that you just need to know is for purely historical reasons. Engineers much prefer to write things using degrees than radians. So this is the type of form that we're going to be using in this class. So I'm going to just emphasize that this is how an engineer would write it. Now, just to be complete, the mathematician, of course, would write it using radians. 3 cosine of 2t plus, let's see, we put 30 times pi over 180. That would give us pi over 6 radians. Notice I'm not drawing the symbol with the radians. You need to draw the little degree symbol if you're going to use degrees. If you don't draw that degree symbol, then you're wrong. Then it's a unit of radians. I'm going to make this a little bit clearer what our mathematician colleagues would call a pi. I'll separate those lines by a little bit more. So this is the mathematician's approach. And please don't draw it that way. Next, still under phase, we're going to talk about leading or lagging phase. An engineer talks about phase. The engineer is really always talking about phase relative to a pure cosine. So I'm going to start off by drawing that pure cosine right here. So this is our pure cosine of some frequency times t. As engineers, we're interested in phase shifts that our circuit does to a waveform. So we're going to put in a zero shifted pure cosine wave into a circuit, and then we'll measure the output waveform. And that output waveform will probably be shifted either leading or lagging. It'll be shifted to the right or to the left. And we want to know how much phase shift there is and if the output is leading or lagging in phase. So I'm going to draw a example output waveform. This output waveform I'm going to draw will be a sine wave. And although it is a sine wave, we know from it is a sine wave of the same frequency. You can see it's the same frequency. But because in this very upper left-hand corner, I said that as engineers, we want to write everything in terms of possibly phase-shifted cosines, I'm not going to call it a sine wave. I'm going to call it a cosine that's been phase-shifted by negative 90 degrees. And my question is, forgetting the numbers for a second, just by looking at the pictures, can you tell me if the red waveform is leading or lagging relative to the blue reference waveform, where the blue reference waveform is always going to be a pure cosine? So here's how to think of it. Take a look at where the waveform in question hits a 0 point. Take a look at where our reference hits a 0 point. Do you see how it took a little bit of time delay for our waveform in question to hit the 0 point? It was a lag in time that it took our waveform in question to hit that 0 point after our reference waveform hit that 0 point. So therefore, we call this distance here, we call this a lag. And so we say here that the red waveform lags the blue waveform. And if we had shifted that red waveform much to the left, we would then say that the red waveform leads the blue waveform. Let's do one of those examples. So here, the green waveform hit 0 before blue. And since it hit before blue, it leads blue. As opposed to the red waveform that hit 0 after blue, and so it lags blue. So no matter where we draw a waveform, you can always tell if it's leading or lagging relative to our reference pure cosine waveform.